So the first point is warping effect. So the frequency warping concept is used in many ways in the literature depending on different topics. So frequency warping of function h of f is performed by applying the unitary warping operator u to the function. If we consider omega and ohm represent the frequency variable in the analog filter and the derived digital filter, then the equation is like this, that is hd of z equal to ha of s, having the values given here, that is s is equal to 2 by 2 z minus 1 z plus 1. It gives the frequency response on a digital filter as a function of the frequency response of analog filter. This equation, what this equation shows? It shows it gives the frequency response of digital filter as a function of frequency response of analog filter. So hd e raised to j omega t is equal to ha in bracket j omega. So it provides that s is equal to 2 by t z minus 1 in z plus divided by z plus 1. So j omega is equal to what? J omega is equal to, again z is replaced by the z is replaced by e raised to j ohm t. So equation will be omega is equal to 2 by t tan of ohm t by 2. So this is the equation. Now for the values less than 0.3 by t, the value of both omega and ohm is nearly equal. So as a result, the digital filter has the same frequency response as the analog filter over this frequency range. Now for higher frequencies, the relation between these two becomes non-linear and distortion is introduced in the frequency scale of the digital filter relative to that of the analog filter. This is called as a warping effect. The frequency warping transformation is a process where one spectral representation on a certain frequency scale and with a certain frequency resolution is transformed to another representation on a new frequency scale. The new representation has a uniform frequency resolution on a new scale, so it has a non-uniform resolution when observed from the old scale. The new frequency scale are related by a smooth and monotonic warping function v of f with positive derivative. Sometimes the frequency warping transformation is shortened to a frequency warping or to frequency transformation. The essential difference between frequency warping and the frequency warping transformation is that first one map the information back to the same domain, whereas the second transform it to the new domain. This function defines how individual frequency component and different frequency ranges are mapped on the new scale. It also defines how the resolution of new representation is allocated, which ranges in the original representation are compressed and which expanded, that is stretched or resolution increased. High values of the derivative dV by dF indicate a range where the spectral representation is expanded and the resolution is increased. Correspondingly, low values of the derivative indicate the ranges of resolution reduction. At the tuning frequency where dV by dF is equal to 1, the spectral resolution is unchanged. So the warping effect changes the band edges of digital filter relative to those of the analog filter in non-linear way, which is shown here. So the frequency warping effect is a capacity H of f performed by applying unitary distorting administrator U to the capacity. A few creators have utilized the idea of distorting in association with U administrator, but that is it may unaltered on the ground that the administrator is H mapping. Recurrence twisting change is where one ghostly portrayal on a specific recurrence scale, and with a specific recurrence goals is changed to another portrayal on another recurrence scale. This effect compresses the magnitude and the phase response. This effect is called as wrapping effect. So pre-wrap our desired digital frequency and substitute that into the transformed digital filter function. Next is Butterworth filter design. The signal processing filter, which is having a flat frequency response in the passband, can be termed as Butterworth filter and is also called as maximally flat magnitude filter. There are various types of Butterworth filters such as low pass Butterworth filter and digital Butterworth filter. The filters are used for shaping the signal's frequency spectrum in communication system or control system. The corner frequency or the corner frequency or cutoff frequency is given by Fc is equal to 1 by 2 pi Rc. The Butterworth filter has a frequency response as flat as mathematically possible. Hence, it is also called as maximally flat magnitude filter, having frequency range 0 Hz cutoff to cutoff frequency at -3 dB without any ripples. The quality factor for this type is just 0.707, and thus all high frequencies above the cutoff band rolls down to 0 at 20 dB per decade or 6 dB per octave in stop band. The process or a device which is used for filtering signal from unwanted component is called as a filter, and it's also called as a signal processing filter. So to reduce the background noise and suppress the interfacing signals by removing some frequencies, it's called as filtering. So there are variety of various types of filters like linear or non-linear, time invariant, analog digital, active passive, and so on. Linear continuous time filters are Chebyshev filter, Bessel filter, Butterworth filter, and elliptic filter. Now, the signal processing filter, which is having flat frequency response in the passband, known as a Butterworth filter. The Butterworth filter changes from passband to stop band by achieving a passband flatness at the expense of wide transition bands, and it is considered as the main disadvantage of Butterworth filter. In Butterworth filter, order increases, then cascaded stages within the Butterworth filter design increases, and also the filter get closer. So the frequency response of nth order Butterworth filter is given by h of is equal to 1 divided by square root of 1 plus epsilon square in bracket w by wp 2 raised to n raised to 2n. The rate of fall of response of the filter is determined by the number of poles taken in the circuit. The pole number will depend on the number of reactive element in the circuit, that is the number of inductors or the capacitors used in the circuit. These filters have predetermined considerations whose applications are mainly at active RC circuit at higher frequencies. Even though it does not provide the sharp cutoff response, it is often considered as the all-round filter which is used in many applications. A Butterworth filter is a type of signal processing filter which is designed to have a frequency response as flat as possible in the passband. So the Butterworth filter is known as maximally flat magnitude filter. Here the frequency response of this filter is flat in the passband and rolls off towards zero in the stopband. The rate of roll-off response depends on order of the filter. The number of reactive elements and used in the filter circuit will decide the order of the filter. The inductor and the capacitor are reactive elements used in a filters, but in case of Butterworth filter only capacitors are used, so the number of capacitors will decide the order of the filter. While designing the filter, the designer tried to achieve a response near to the ideal filter. It is very difficult to match the result with the exact ideal characteristic, so we need to use a complex higher order filter to achieve the characteristic near to the ideal filter. If you increase the order of the filter, the number of cascade stages with the filter is also increased, but in practice we cannot achieve Butterworth ideal frequency response because it produces excessive ripple in the passband. The characteristic of normalized Butterworth filter frequency response are very close to ideal near omega equal to 0 and equal to infinity, very smooth at all frequencies with monotonic decreases from omega equal to 0 to infinity. Largest difference between the ideal and actual response near the transition. Next is Chebyshev filter. These filters are used for distinct frequencies of one band from another. They cannot match the Windows Sync filter's performance, and they are suitable for many applications. The main feature of this filter is their speed, normally faster than the Windows Sync, because these filters are carried out by the recursion rather than convolution. The designing of this filter, designing of Chebyshev and Windows Sync filters depend on the mathematical technique called the Z transform. These filters are classified into two types: one Chebyshev filter and type 1 Chebyshev filter and type 2 Chebyshev filter. These filters are analog or digital filter having a stepper roll off than Butterworth filter and have passband ripple or stopped ripple. These filters are nothing but analog or digital filter. So these filters have a steeper roll off and type 1 or type 2 the Butterworth filter. The property of this filter is it reduces the error between the characteristic of the actual and idealized filter. As these are analog or digital filters having a steeper roll Butterworth filter and passband ripple or the stopband ripple, the Chebyshev filter have the property that they may minimize the error between the idealized and the actual filter characteristic over the range of the filter. Because of the passband ripple inherent in this filter, filters with a smoother response in the passband but a more irregular response in the stopband are preferred for certain applications. Type 1 Chebyshev filter. This type of filter is the basic type of Chebyshev filter. The amplitude or the gain response in an angular frequency of the nth order of low pass filter is equal to the value of the transfer function. The order of this filter is similar to the number of reactive components required for the Chebyshev filter using analog device. So the amplitude of the ripple of 3 dB result from epsilon equal to 1. Type 2 Chebyshev filter is also known as an inverse filter. This type of filter is less common because it doesn't roll off and needs a various component. It has no ripple in the passband but it has an equiripple in the stopband. The gain of this type of filter is Gn in bracket omega 0 1 by square root of 1 plus 1 divided by epsilon 0 Tn 0 omega 0 by omega. Next is elliptic filter. Elliptic or the elliptical filter is also known as a Core filter and sometimes even a Zolotard filter. This filter is used in many RF applications where a very fast transition between the passband and the stopband frequencies is required. The elliptic filter produces the fastest transition of any type of the filter, but it also exhibits a gain ripple in both the passband and the stopband. The key application for this filter is for situations where very fast transitions are required between the passband and stopband. It could be that spurious signals fall just outside the required bandwidth and these need to be removed. Sometimes where non-amplitude sensitive forms of the signals are used, a form of gain equalization may be possible to counteract the ripple of the RF filter. The characteristics of the elliptic function filter are best described in terms of 4 parameters that specify the frequency response. The first one is maximum variation or ripple, the width of transition band, the maximum response or the ripple in the stop band, and the order of the filter N. Thank you.